Okay, so final exam is it Thursday at 1:10 p.m.? That sound right? Okay. And this guy is going to be 10 questions. Take about an hour. So normal exams, 10 questions, designed to take an hour. You have the full hour and 50 minutes to take it, so should not be a time crunch. So even if you're if everybody else is finished, don't feel rushed. You have the entire hour and 50 minutes for your exam, so feel free to use it. So it'll look a lot like the midterm in terms of length and all that stuff. Remember the policy, if you do better on the final exam than you did on the midterm, I'll replace your midterm exam score with the final exam score. Not the other way around, though. Okay, so what I'm going to do, any generic questions about the exam before I start going through the slides, telling you what I think is important and what's less important? Okay. So as a starting point and a promise in here, so it's pretty much always a given in my exams that you'll have at least one conversion question. You will likely have several conversion questions in here. All right, so prepare for that. We'll talk about the nature of them. For in here, conversion questions could come in the form of converting between bases as well as converting between sizes. Okay, so if I asked you, how many kilobits in 17 gigabytes, you should be able to do that conversion. Similarly, you should be able to convert from, decimal to octal or hexadecimal to binary and all that jazz. You might want to review the tricks, the hex to binary and the octal to binary and vice versa. Those tricks, because there very well might be a question on the exam. I think there was on the previous exam, right? Question on the exam that will be quite easy if you know the trick and painful if you don't. Not that it's not doable if you don't, but it will be somewhat painful. All right, so in fact, you might even remind yourself that if you have a question that has if you see a lot of bits on the screen, a lot of bits on the test, chances are there's a trick involved. Okay. If I've given you I've actually written a 64-bit binary value, probably a trick. Okay, because your calculator might have issues coming up with 2 to the 64th or something, or 2 to the 63rd, I guess. All right, so a majority of the exam will be stuff we've done since the midterm, but there will be some stuff before the midterm. So I'll just go through all this and kind of say which things still pop out in my head. There could also be a couple of things since before the midterm that were not on the midterm that, if they were important enough, might make an appearance on the final. But I'll try to highlight those things here. Nothing about computer parts. Nothing about history of CPUs. You should certainly understand what a CPU is and all that magic tricky stuff, but I'm not going to ask you anything about the old CPUs. The whole list of magic tricks, the architecture of a CPU in terms, we've been dealing with the ARM instruction set, so that stuff would be fairly important. And we'll review that here in a few minutes. Probably wouldn't ask questions about why magic tricks at this point. That was probably up to midterm type stuff. We'd be focusing more on changing the state of memory, changing the state of registers through using these magic tricks. Nothing on clock speed, nothing on VLSI. There could be an outside possibility if I was looking for kind of a short answer-y type question of something involving single core versus multi-core from the perspective of how many instructions could be executed at one time. Okay, so kind of think about this more recently in terms of, and this would maybe be a question where I give you like a scenario and ask you to maybe discuss challenges or something with it. So think about our, more recently, we have our interpreter we have written in Android, and we're going through it line by line by line by line. But the reality is inside of that interpreter, we are presuming those instructions happen individually, one after another, sequentially, right? Well, if we had this running on multiple core CPUs, there's a possibility that two different instructions show up to two different cores at the same time, and it's possible one of those instructions is actually reliant on another one. Okay, so if this instruction here is supposed to load into a register some value from memory, and this instruction here loads into memory a value that this guy was relying on, now we have a race condition of, is that value there, or do I grab that default value or whatever was leftover value from memory and bring it into the register? All right, so that would be kind of an example of a single core versus multi-core question. So less about the hardware and more about kind of the what you need to be careful of when you're executing instructions, when one instruction might be reliant on another instruction. Okay. Low priority. I don't anticipate asking that question, but those, I do like multi-core type of topics. So if I was looking for a question, that would be on the docket. Nothing about benchmarks. You should understand the benefit, the pros and cons of hardware versus software, but I doubt I'll ask about it. Hardware is fast but inflexible. Software is slower but flexible. Pretty straightforward. Nothing there. Probably won't ask anything about the types of instruction sets. We pretty heavily cover like RISC and stuff like that through the midterm. Should be fairly straightforward. Same thing we just talked about a minute ago. Nothing from that. All right, so definitely familiarize yourself with this. I would say memorize this, but if you just look at the pattern, you can pretty quickly see that everything is a scale from the left column to the right column is a scale of 8, and everything in an individual column scales by 1024. So you should be able to reproduce this chart pretty quickly, right? So on the exam, I might give you a value like in gigabytes or something and ask you how many kilobits. So make sure you pay attention to the big B versus the little b, that kind of stuff. So there would probably only be like one of those. I kind of want to make sure I'm testing keep in mind the purpose of an exam. Okay, so I'm not going to trick you. I'm not going to purposely trick you on the exam. So if you feel like you're being tricked, then chances are I wrote the question poorly or you're not understanding what I'm asking. So in that case, don't guess, come up and ask and I'll clarify. But the purpose of an exam is for me to measure your competence in the material. Okay, and generally speaking, especially in a final exam, you're kind of thinking about this from the perspective of what questions might be on a final versus what ones might, and not just my finals, but this probably goes for all of your classes. I remember when I used to study for exams, I would go through the notes and kind of write a sheet that says, these are the things, almost like what I'm doing now, but these are the things of what I think the teacher thinks is important, that kind of stuff. So remember, the purpose of a final exam is for me to effectively measure the competence of what I think you should get out of this class. So there's some extraneous things in there that, while they might be interesting, maybe aren't one of the big concepts that are super important, that kind of stuff. So in general, I would be surprised if I ask something that is very far off the reservation. Every now and then I do, because in my mind I thought I talked about it quite a bit and then I actually didn't. So I mean, that's happened before. But in general, if you feel like you're being tricked on the exam, ask for clarification, because that's not my intent. All right. So there'll probably be like one question for converting sizes, just because I want to test your competence that you understand when somebody says something is a 64-bit register. What does that mean? What's the idea of 64 bits in terms of storage? And I'm going to make you show that by moving between different sizes, proving that you kind of understand those concepts. Okay. Yeah. So this kind of thing. Definitely the concept of memory. Certainly, there could be a question on there that deals with, the closer to the CPU the memory is, the more expensive, the smaller and the faster it tends to be. That was represented in a question on the midterm, so pretty unlikely that I'll ask the same question again, unless it was a question that was missed a lot. So I haven't gone back and looked at the midterm, but you might look at the midterm and remind yourself if there was a question on there that was missed heavily. There's a decent chance that concept will be asked again on the final. So I'll go back and review the midterm as well, but I don't recall it off the top of my head. So you might go back and look at that. All right. So again, it would be fair game for me to ask you about this, but I did ask you about this on the midterm, so I probably would not on the final. Nothing about pixels. Getting into the ARM architecture, that's going to be heavily represented on the final. All right, so the idea of what it means for a register to be an 8-bit register or a 16-bit register. When I say know what a register is, what's the purpose of a register, that's kind of our starting point for where the CPU eats, right? So we load things into registers before the CPU can operate on them because registers are the fastest memory we have. That's kind of our punchline. So even just more recently, we think about our loads and our stores. The whole purpose of those guys is we have a big collection of system memory, right? That we consider by human standards as being very fast, but the reality is that slow compared to a register. Very slow compared to a register. So with that in mind, when we load things from memory into a register, we're using our memory for relatively long-term storage because we have a lot of it. And we're using our registers as our launching area for when we want the CPU to take over and actually execute one of its magic tricks. All right, because we have relatively small amount of memory in registers relative to our system RAM. All right, but and also along the idea of signed and unsigned, know the difference between a signed number and an unsigned number. Be able to do the math of 2's complement. In fact, I can almost guarantee there'll be a question on there. It might be I give you a binary representation of a value encoded in 2's complement and ask you what the decimal equivalent is. I think that was a question like that on the midterm. Might be the other direction, where I give you a decimal number and ask you to give me the 2's complement version, but 2's complement will be on the exam, one way or another. Okay, in a calculable question, not a what is 2's complement or what's the advantage of 2's complement over 1's complement or sign in magnitude, which is, we only have one representation of 0 in 2's complement, so that's considered better. So we don't waste the spot to have a -0 and a +0. This one, I think I said the exact same thing before the midterm. You should be familiar with nibble and byte. Anything bigger than that is relative to the architecture. So word and double words, I think we came up with these values. I think he helped us come up with these values from the book, but I won't ask you about. I will never ask a question in terms of word or double word. But bytes are always bytes. Okay, bytes are 8 bits, and nibbles are always half bytes, 4 bits. So those 2 words you should be familiar with. There's no promise I'll use it, but I'm allowed to use those 2. is the punchline. Okay. If I use like a made up word, come and ask me because it might be that I made it up. But in general, I try not to ask the questions in a confusing way. So definitely understand the concept of arrays, but not from the programming language side of things, but from the base address plus offset side of things, like we've been looking with stores, stores and loads, right? So that stuff we have experimented with recently in writing our assembler, and then learned about theoretically before that, right? We store a base address in a register, then we say go to this base address by an offset of something, put something in memory there or read something from memory there. That's how arrays work anyways, right? When we define an array in a standard programming language, new is our real estate agent, so AR would be equal to the base address of this array. And then when we say go to bucket 3, we're going to say go to the base address, then jump an offset of 3 to get us to the actual value we're interested in. That make sense? Okay, so this is evidence of architecture matching up to your programming languages. You're seeing the backside of it now. All right, so we've kind of made a triple-decker sandwich. I taught you, here's how arrays work. And then I said, this is how they actually work under the hood. And now you're seeing this is how hardware actually works under the hood. And these two match up. Okay? So understand that concept. It's possible I might reference that relationship to arrays in a normal programming language. It's kind of like what I just talked about here. But certainly be familiar with load and store syntax for, or even the concept of base address plus offset for walking through memory. And even if there's a kind of a bigger cadence, I think we have a slide that mentions it, but it's in my head right now, so I'll just mention it out loud now. Just that kind of our bread and butter memories. You know, we've talked about caches and things like that, and that's all fine and good. But, you know, we just look at cache. You know, we've kind of talked about the high level as cache just being a way of maybe expediting getting values into registers. You know, but it's kind of, we're reliant on the operating system to use those things as fancy, you know, using fancy tricks. Okay, I'm probably not going to ask you about caches from that perspective. You know, it's just a high-level concept. They're there if we want them to be, if we want them to be, because they are faster than system memory and larger than registers. That makes sense? Okay, but really, if we just think about the normal cadence of getting information to our CPUs, we store stuff in system RAM for bulk storage, and we store stuff in registers when we're preparing it to enter the core of the CPU. Okay, so almost all of our moves are from register to RAM or RAM to register. Okay, so those are our kind of our go-to moves. So anything dealing with ARM instructions and stuff like that is going to be focusing on those two things. So some just, again, this is in my head now. Just like in a lot of the programming classes where I'll give you like, here's some code that does something. I might give you some, well, I promise you, I will give you some assembly code in terms of the things that we've kind of spent time on, or I will give you a list of instructions and what they do. So if I use an instruction that we haven't like implemented in our interpreter or in our assembler, I guess, I will give you the syntax for that guy, and I might give you some code that does something, and then ask you to show me what the final state of registers and the final state of memory is. Following that, similarly, I might ask you to write some code that performs some operation in terms of the magic tricks that we have. You know, kind of our bread and butter magic tricks we've worked with recently, or from a list of magic tricks that I give you. Make sense? Okay, and it's even possible if I need to kind of force a question, like I want to accomplish something that isn't easily accomplished by the normal ARM architecture, I might even invent an instruction. So they say does this because that's what I needed to do. Okay, so, but I would provide that to you on the exam. I would say, here's the instruction, here's the parameters, this is what it does. Okay. So understand load versus store. So we load things into registers from memory. We store things into memory from registers. All right, and we do that in terms of a base address plus an offset, where the offset can be 0. We just want to go to the base address, but there actually is a way to just go to a certain thing, but we've looked at loads and stores with offsets. Conversion stuff, make sure you know how to do that. Be very familiar with hardware registers. I probably wouldn't ask you a high level question like, what is a hardware register? It would always just be comfortable using them. Won't ask anything about embedded systems or Internet of Things. Probably wouldn't ask anything about this. I'm going to have enough other questions to ask about conversions and code and things like that. Just kind of when we talk about a CPU architecture, what are we really talking about? We're talking about the instruction set that it implements as well as the hardware components about that architecture. How many registers there are, and then how many and how big are the caches. But those are really, especially with the cache, those are things that the operating system itself is going to use for determining how do we optimize the processor to get instructions loaded into the processor as quickly as possible. So if you're using one of these server class chips, I think we mentioned this a couple of weeks ago or something like that, that kind of the difference between a server class chip and kind of the equivalent consumer class chip is likely maybe the existence of an additional cache, but more often than not, size of cache. So in a consumer chip, you might have 128K kilobytes of, let's say, something like L2 cache, whereas in a server class, you might have 4 megabytes of that same cache. So a lot more in terms of a percentage, and a lot more in terms of dollar signs. Okay, but the more L2 cache you have, so you have 4 megabytes of it, the more stuff you can store in there ready to be loaded into the registers. Make sense? So consider if our registers are like 32 or 64-bit registers and you have 4 megabytes of, let's just call it super fast RAM. That's what cache effectively is, right? You could throw more stuff into that than if you only have 128 kilobytes of cache. So you can get more stuff loaded in. Now, you might say for a single user, maybe that's not really that beneficial because we're not needing to do that much optimization. But a lot of times when we think about server class machines, we're talking about a machine that's serving multiple users and multiple running user programs at the same time. Therefore, it might be beneficial for us to have a lot more cache. And where it really comes into play is with L3 cache. What's special about L3 cache versus L1 and L2? Go ahead.
It's shared between cores.
Yeah, so L1 and L2 are on a per core basis, right? But L3 cache is kind of our singleton, our hardware-based singleton that allows us to share stuff between all the cores. Okay, so if you get a really large chunk of L3 cache, now you can start storing a lot of information that whichever core is ready to process the next magic trick can grab from. And that can be pretty powerful in a multi-user server environment, and that's where the additional cost of those server processors is worth it. But if you are just building your own machine where you're the only user and you have a chip that has 4 megabytes or 16 megabytes of L3 cache, it's a pretty expensive thing you're not using. Is what it comes down to. This is the way it works. Okay. Again, I mentioned before, so I won't mention half words. I won't mention word or double word, but bytes and nibbles would be vocabulary I will use on the exam, or I'm allowed to use. So understand 8 bits is a byte and 4 bits is a nibble. And anything bigger than that, I'll say something like it's a 16-bit register or it's a 32-bit register, something like that. Okay, so here's kind of our looking at loads and stores from the theory side of things. So we're storing things into memory, starting from a base offset. So load into, so we have X2, some register has a base memory address of 100. So this might be this guy. And then we're going to offset that by 4. So we're going to take a step of 1, 2, 3, 4 and put a value there. All right, so that's how we address memory. Understand immediate values. These are effectively, from our perspective, integers, right? Hard-coded values. And they're used with our immediate versions of our add and subtract And there's other immediate things, but those are the ones that we have used. We also use immediate values for offsets, although I don't think the syntax actually dictates them as being immediates. I think it's called them offsets, but it effectively is a whole number. All right, more conversion stuff. You should be able to do left and right shifts. I certainly might put that on the exam. I'm not a huge fan of it. We don't have, in the graduate architecture class, we do a lot more with doing things with shifts for scaling values. But in here, we kind of we have a concept of, okay, we shift left we just move bits, and shift right, we move bits, and okay, that's all fine and good, but why? So pretty low priority that I'll put a shift question on there, but it'd be fair game. Okay. I suppose I could ask a question like, what is the net outcome of shifting left 3 times? Or what is the net outcome of shifting right 2 times? Something like that. So when we shift left 3 times, we're effectively multiplying our value by 2 to the 3rd power. So it scales it up, right? So because we shift everything left 1, then 2, then 3. So we've actually multiplied whatever the decimal version of our original value was, we're multiplying that by 2 to the 3rd power in that case, if we're shifting left by 3. Similarly, if I shift right, I'm dividing by 2 to the number of shift to shrink a value down. Make sense? So if I asked a question related to shifts, it would probably come in that form, as opposed to me asking you to perform a shift. And I would ask a question more like that if I kind of felt like the exam was already floating around like a 1-hour exam, and I kind of needed like here's a question that you either know or don't know, as opposed to a mathy, let's solve something question. Go ahead.
So you said left is multiply, right?
Left is multiply by 2 to the power of number of shifts. Right is divide by 2 to the power of number of shifts. I do like bitwise operations. So performing a bitwise operation might come into play. We did a bitwise on the midterm. What I might do is kind of give like a combination type question where maybe I give you 2 values and say, perform a bitwise OR on these 2 binary numbers and then convert the result to octal. Something like that. You know, something that just kind of combines 2 skills. So a little bit more than just doing the bitwise and or. All right, so be familiar with loads and stores and how those guys work. Understand the purpose of this syntax. ARM makes this nice for us by this guy kind of looks like an array, right? So the ARM syntax kind of looks like an array, a C-based array syntax. So that kind of reminds us that, oh, this is how arrays have always worked. So we're going to go ahead and treat this as a base address plus an offset. Again, the storing negative numbers, the only representation will be 2's complement on the final. I think we're all on the same page with the sign and magnitude in 1's complement, but 2's complement will be on there. A kind of a reminder here for like the tricks I mentioned earlier to make sure you make yourself familiar with the number conversion tricks. So 4 bits is used for binary to hex and hex to binary, whereas 3 bits is used for octal to binary and binary to octal, right? Because 3 bits can represent the numbers 0 through 7, and 4 bits can represent the numbers 0 through 15, which just happen to be 0 to 15 are the legal values in hex. 0 to 7 are the legal values in octal. They're very compatible numbers. And there's your rationale for why octal is popular for computers. Otherwise, you know, a lot of the alien novels I might read, all the aliens seem to have 8 fingers. It's like a thing. I don't know. I think they just try to come up with fascinating, you know, ways to kind of just bring that in, like, oh, they're on the base 8 number system. They're so smart or something. I don't know. It seems to be a thing. I don't know if you don't read novels like that, but a high percentage of alien books have them with 8 fingers. It's a thing. Well, total of 8, 4 fingers per. All right, so understand the nibble aspect of this, even though this particular slide is looking at it from a sign and magnitude thing. Just know that 4-bit thing is relative to hex. Okay? Be able to do 2's complement, representing signed numbers. Be able to encode a negative number into 2's complement. Do you need to encode a positive number? No. So positive numbers are just stored as their binary equivalent. Negative numbers are stored as the binary equivalent encoded 2's complement. All right. Similarly, if I give you a number that I say might be encoded in 2's complement, or it's stored as 2's complement, you look at the far left bit, right? The far left bit is a 1. You know this is a negative number, therefore you need to decode it. If it's stored as a 0, you know it's actually a positive number. Decoding is not necessary. You can just convert it back to decimal. Make sense? Also remember the trick for decoding and encoding. So when we encode 2's complement, we flip all the bits and add 1. So we might say to decode, we subtract 1, then flip all the bits. But you can actually do what? Add 1, then flip the bits. So you can always accomplish it through adding. Actually, it's flip the bits, then add. Yeah, so you flip the bits, add 1 to get you to the encoded value. Then you flip the bits and add 1 to get you to the decoded value. Or I think I said it backwards the first time. Okay. It would be fair for me to ask a question like, what are the range of values that can fit in the 2's complement representation of a certain size number? And I would probably, I'm not asking you to memorize this. I would probably ask you to, so I might say, assuming you were storing values in 6-bit numbers, something like that. What is the smallest value that would fit in 2's complement of a 6-bit signed value versus the largest value can fit in a 6-bit unsigned, or a 6-bit signed value on the positive sign. So that is, if I'm doing 6 bits, what's the smallest value that would fit in 6 bits?
0.
6 bits signed.
64.
What is 2 to, yeah, so 64. So it'll be negative 64 to positive 63, right? So if I say, what's the smallest value that'll fit in a 6-bit signed number? It would be negative 64. What's the largest value that would fit in a 6-bit signed number? It would be positive 63. Yeah.
What would be 32? There's an 8.
Oh, yeah, 32. Sorry. Yeah. Negative, yeah, because it's 2 to the 6th is 64, but we actually are only using 5 of the bits. So this is actually 2 to the 5th, which will be negative 32 to positive 31 for 6 bits. If I had said 7 bits, it would be negative 64 to positive 63. All right, I think this was mixing from another class. Oh, maybe not actually. No, because we were actually it was from earlier in the thing. Yeah. So in normal programming classes, we're talking about high-level stuff. In here, we're talking about low-level stuff, mapping to machine stuff. So understand that idea of mapping. I probably would not ask you on the exam because I'd have to give you the documentation for like what that instruction is. So like remember the opcode is stored as an 11-bit number, right? So you would convert, like add I, you would represent that in its 11-bit representation of what is add I in the list of instructions for ARM. Well, I'm probably not going to provide you with the list of instructions for ARM because it'll take too many pages. And then at the same time, I'm also not going to ask you to memorize that. So if that question popped up, I might ask you, what is the breakdown of how a machine instruction is stored? Something like 11 bits, followed by their 5-bit registers. And then there's a shift bits. But I really think I probably would not ask that. I'm going to have enough other stuff to ask, and that's really just knowledge you could pretty easily look up, right? Not really testing competency, just memorization. So I probably would not ask that. Again, the shortcuts, make sure you're good with the shortcuts. Yeah, here's that instruction thing. So let's call this fair game in case I get really desperate, but I think it's unlikely that you would have to know the 11-bit thing. But in fact, I'll just say I'm not going to ask it. I'm not going to ask that. I have enough other stuff. All right, so now we're getting into our emulator, okay, that we wrote. So AR map was our big, singleton type thing. This was things that we had from our twos complement stuff. So I need to get back. This is more conversion because I think sometimes when I click on the wrong slide to begin with, I started inserting stuff in weird places. Sign and magnitude. Load should be fine. Convert. Be able to do bitwise XORs, bitwise XORs. So one over the other, but not both. So understand the difference between bitwise and, bitwise or, bitwise XOR. This could find its way onto the exam. This is kind of the how does your computer work? When you double click on an icon, what happens? Software application is found on the hard drive. It is partially, at least partially, it depends on operating system, but partially loaded into system memory. And then from system memory, things are then brought into registers for the CPU to process. Now that's kind of the cadence. So if I asked you kind of a high level question of, from double click to CPU executing a magic trick, what has to occur? Something like that. All right. Similarly, what does memory look like? I mentioned earlier, I might give you some sample code and tell you to show me the state of registers and state of memory afterwards. So memory kind of looks like a giant array, correct? So if the particular code I gave you, was messing around with memory starting at address 100 and was putting stuff into address 100 through 112, when you show me the memory afterwards, you would probably just show me that little snapshot of memory between 100 and 112, labeling it saying, well, at base address 100, we have this value, then here, then here, then here, and register X0, X4, and X13 changed. Something like that, okay, as opposed to showing me the current state of all 32 or 64 registers and all of RAM. So you can just show me the highlights of those couple of places. So generic syntax for load. You're posting stuff during my class?
No.
Yes, you were. yes, you were.
Well, if you asked, have to be
I was bringing awareness to so move Z, move K. This was getting a value. So what was the difference between move Z and move K? The Z and the K meant what? Kind of talked about this, I don't remember if it was last class or the class before, as maybe a trick for utilizing the high and low portion of a register. So move Z, the Z stands for what? Somebody else? Zero. Okay, what does that ultimately mean? So zeroes out the register first, then move stuff, right? So we're dealing with a clean slate. So you're right, effectively deletes what was there. Okay, move K, what's the K stand for? Keep. Don't zero it out first. So whatever you had in there, leave it alone and then put the new value in. That can allow us to do a high and low portion of the register, right? Where if we load something in, it's only taking the far right 8 bits. And then we put another value in that's taking the far left 8 bits and we move it with a K for keep. We could actually have a high and the low portion of the register holding 2 separate values if we became desperate in, not using too much memory. Yeah.
For move K, if you were to move another value into the high, that's like already got something in there. Would it essentially do a bitwise OR on the 2 values?
No, it would just overwrite individual bits. Okay. Yeah. So don't do that. I mean, if you're going to do it with the knowledge of that. So you'd want to, you might decide to move in there. Let's see, how would you do it? Because you wouldn't want to use a move Z. Because you wouldn't want to automatically zero everything out because you don't want to mess up your low bits. Ooh. You would have to probably do your own bitwise OR on the second half to get you so you'd be dealing with a duplicate of the second half, and then load zeros followed by duplicate, overwriting the entire register so effectively zeroing out only top half. Zeroing out the bottom half is fairly easy, but zeroing out the top half is more difficult because you don't want to lose what's in the bottom half. Yeah, won't be asked on the exam, but it's an interesting question. And realistically, there are probably ARM instructions that allow you to specifically work with highs and lows halves. We didn't look at them. There is, well, actually, the way Intel assembly does it is there's a register like X0 would be called AX, let's say, in Intel assembly. And then you can deal with AH and AL. So it allows you to kind of talk about the registers in terms of the high and the low of it. I don't know if ARM supports that, but I would be surprised if it doesn't have something similar to allow you to operate with portions of a register. But in the absence of that, you could do binary tricks to make it sort of work. Okay, and we like binary tricks. They're fun. All right, so move Z, move K. Be familiar with both of those. So it's possible I might give you a value. And, I might say that a current register has, X0 has this number in it. And then I say move K, some other value into it. You'd have to know that inside the registers, they actually are stored as binary values, not as decimal. We like working with them in terms of decimals, but they're actually binary. So if it already has a binary value and I'm having you move K into that, you'll have to make sure that you do the conversion to binary and give me the final state of that register, knowing that the bits that were already there are kept and only the differences are rewritten or overwritten. Make sense? Similarly, know that move Z gives you a fresh register and then moves the whole value in there. Move Z is the one we implemented in our code, and we did that for this exact the reason I just mentioned, is that in our Android app, we were dealing with everything as decimal because that's friendly for us, right? But the reality is it's dealt with in binary. So we could have written it. In fact, we started writing the preparation for storing stuff in binary in our assembler, but we didn't do move K for that reason. It would have been difficult for us to play the game of keeping the bits. We could have. Actually, wouldn't have been that difficult. We could have done it with decimal, but it would. If we had like the number 37 stored in a register, we would have converted that to binary first. And then if we were trying to move K 21, we would have converted 21 to binary. And then we would have just overwritten the differences of the bits, leaving us with another binary number that converted that back to decimal. So then it would be hard to test. It's like, is that right? Chances are the answer is yes, but if you have 36 and you move K 21, you might be left with a 49 or something, something like that. And you might just say probably right because now you got some extra ones mixed in there, or at least potentially, stuff like that. All right, so that was our discussion of putting more than one thing into a register. I would not ask you to do that on the exam. So on the exam, you won't have to do something like load the number 17 into the high side of the 8 bits of a register or something like that. Appreciate that it can be done with some binary tricks, but you won't have to do that. You'll always be using registers in their entirety, with the closest cousin of that caveat being you should be able to deal with move Ks, where understand that you're dealing with binary numbers and you are keeping the bits that were already there and only overwriting the difference. Okay, so questions? Anything you want me to go back and cover related to the exam?
You have to write any Java emulator stuff?
No, I can't imagine that. I mean, like stuff from the actual Android app?
Yeah.
No. I mean, the purpose of the Android app was to implement those instructions, not to learn Java. Yeah. So if there was anything on the exam that looks like high-level programming, it might be something that looks like an array based on one of like the offset questions or something. But yeah, you won't have to write any high-level language on the exam. I just want to make sure that's clear. So the reason we wrote the interpreter is to look at the implementation of how those commands actually work, not to practice Java. And then the other benefit for us is it allowed us to work in a larger project than we're typically used to working in, and that made it feel more uncomfortable. Yeah, but I'm not testing you on Java stuff in here. What else? Go ahead.
So you said you might have us write a couple assembly programs. Would we have to do any branching?
If you had to do anything like that, I would give you the instruction.
Okay.
Yeah, so like a jump instruction or something like that. So realistically, probably not. Again, this kind of comes down to what competence am I testing. I probably want to say, write the necessary code to accomplish some things and leave inside of X5 some value, something like that. So there might be a couple different ways you can accomplish it, but ultimately it's the idea of each instruction might have likely, or at least might be modifying memory or a register in one way or another. What is the final state of things? And make sure they match up to what I'm kind of requesting, or if you're reading code, show me what the final state of registers and RAM is. Yeah, so I mean, what he's talking about with jumps or branching is kind of like the implementation of if statements. Okay, in order to do that, we need to be able to do Boolean expressions. They're not hard. They're just test instructions. Does this test to a 0? Does this test to a 1? It's still just mathy stuff. If it's a 0, branch to here. Otherwise, branch to someplace else. Usually if it's a 0, just keep going. If it's a 1, branch, kind of jump 14 lines of code. So don't execute those 14 lines and go to the else of your if statement. Makes sense? So it's nothing fancy. It's just what's the next instruction that I execute. Okay, we just didn't actually look at branches, but there's nothing overly fancy about them. All right, what else? All right, so we're all good for the exam? Okay, so then homework for today was to finish up our add the special thing. How did that go? Not too bad. Okay, so let's look at that here for a few minutes. Probably would have been beneficial to use kind of a singleton maybe to accomplish that guy. So let's do... I think we started off on that second screen. We're already, you can click on one of the things and it prints out to the logcat what the dude you selected was, right? So now it's just a matter of, instead of doing that, having it go back to the previous screen and having it add that to the end. Okay. All right, so the real catch here is when we go back to the previous screen. So there's the challenge in this assignment. Actually, let me just get it to the singleton part, and then we'll talk about the challenge, and you can tell me what potential solution you came up with for that. Let me just run this real quick, and I think these guys all print out the right things right now. I just want to confirm that. Now, while this is loading, so Grace, how much money are you competing for tonight?
Yeah, 2,000.
Two-
They said they have more than 2,000.
They have more than 2,000?
Yeah.
That's actually good. Do you know what that probably means? If you don't win, you still get money. Yeah, so, and you're both presenting?
Yep.
So do you want people to come watch or not watch?
They can walk.
Yeah, we should all go and watch. So CU launch tonight, the final competition. Grace and Maddie have an app that they put together, and several other people kind of helped out with working on it too. Alexis was involved in a lot of the brainstorming, and they're giving a presentation tonight at CU launch for a competition, and to try to get some money for like a startup business. And it should be, I think it's at 6 or 6:30. 6:30. But you don't know which group you are, like what number you're presenting or anything. You're just.
No, if it's according to the list, I think we're third.
How many total groups are there?
5.
Okay, so you need to beat 4 other groups. So.
Or 3.
Oh, that would suck to be the one group that doesn't get any money.
Yeah.
Okay, don't be that one. No. I don't know that they've ever. I think the very first time they ran it, I think the grand prize was 5,000, and every other group got 1,000. So if you didn't win, you all got a grand as a starting point. So I would be really surprised if they have like 6 groups and they give 2,000 to the winner and then 1,000 to like the next 3 or 4 and just let one person out. I feel like they would just take whatever they have left and just divide it up against like among the losers, right? But you don't have to worry about it. You're gonna win, right? Yep. See, so go and watch them win tonight at 6:30 It's over in the pharmacy.
No, CC. Yeah.
Oh yeah. So you got to walk outside for this one. Yeah, the environmental of the building. Am I pointing? I'm probably not even pointing in the right direction, but yeah, I am. It's over there. Yeah, so out over there by the lake. So that should be fun. And in the future, I encourage all of you to get involved in the CU launch entrepreneurial thing. It's a good experience, and win or lose, you learn quite a bit and kind of get involved with kind of that entrepreneurial business plan type stuff. And Good experience, you think?
Yeah, I knew nothing about how to do a business model or anything.
Yeah, and our dean of the business school, Dan Sem, is he kind of heads a lot of the entrepreneurial stuff. He's really good with that stuff and is very collaborative with other departments. So take advantage of some of those resources that you have here for getting involved in some of that stuff. I mean, is their app going to turn into some multi-million dollar business? Well, let's say maybe. But even if it doesn't, it's a learning experience, right? You know, it's most companies fail, but you might as well get the education out of it. You're already paying a bunch in tuition. Okay. But I'm sure they're going to win and they're going to be a multi-million dollar company. So this is all moot. I'm talking about other companies.
So you're saying they've got the next MySpace?
I don't know, well, probably better than MySpace. You hope it's better. Did MySpace ever make money?
I think so.
I wonder if they get royalties just off name drop now.
He sold in 2008 for like 5 billion.
MySpace, did they?
I think 5 billion of it.
Yeah.
Yeah, it's mainly a music thing now.
Well, I didn't know anybody still used it.
Yeah, a lot of bands have a MySpace.
You feel like it's almost like a joke that kind of caught on. It's like, oh yeah, visit my MySpace page. No, really, my MySpace page. And then also like, oh yeah, aren't you on MySpace? Just watch. Like in 15 years, it's going to be like the next big thing. You know, kind of like HTTP making its comeback with RESTful APIs. You know, HTTP sits there for 30 years dormant. You know, we just use gets and posts for just normal web requests, and all of a sudden, every single API on the planet's using RESTful calls using the HTTP protocol. So that's it. MySpace is a sleeper. You heard it here first, folks. Okay, so we hit this little add instruction guide. Takes us here. If I hit add I, it shows us what that dude is. So based on what we select here, we want to set something. Probably set a singleton somewhere, right? Reasonable enough way of doing this. Well, depends on how you accomplish this, I suppose. For right now, let me just set a singleton. That gives us, we already have a singleton, first of all, and that gives us a nice little platform to operate off of and make our next decision, right? Okay. So plus I could just throw a, instruction to add into it, and it takes 2 seconds. So we'll go and do that. So I'll go into my AR map. That's my name of my singleton, right? AR map, and right here at the top, just so I don't lose it, private static string instruction to add, and we'll start this guy off as the empty string. So punchline is when it's the empty string, we don't have instructions to add. is the deal, right? What's this?
Why is it private?
You don't want it private. Good question. I made it private specifically for that reason, and you get a star for the day. Yeah, I need it to be public, otherwise we can't access that guy, right? Okay. Now we're good. Or I could also go the route of saying you always make your variables private, then only loosen the reins as you need to, and we needed to. Yeah, so I've protected myself twice there. Still no bugs. still no bugs.
One day you'll find that moth.
Probably. Instruction picker activity. There. All right, so here's our, we're printing it out right now, but instead we're going to say AR map dot instruction to add is equal to the mappy dude. So that'll be the instruction that we are going to add there. All right, and then we can go ahead and probably just go back to the previous screen, because ultimately that's what we want to do, is get back to the previous screen. Okay. Now, what we'd love to happen is when we're back on the previous screen, we'd love for that thing to update. So now we got to think about how can we accomplish this. All right, so let's just get us back to the previous screen first, then we'll think about how can we have done this. All right, so I'm going to say this dot, I think Emma told us that the correct way to end a thing is finish, right? So we'll go ahead and finish it. You could also say call the go back function and as if the back button was pressed and do nothing. For all we know, they both use the same thing, but whatever. So this will take us back to the previous screen. So let's go and do that. Make sure it gets us back to the previous screen. All right, click one of these guys, and it takes us to the previous screen. All right, now we'd really love for it to get added to the bottom here. So if I just hit clear, we can do that. So what we'd like to see happen is if we're starting like this, I click something, comes back here, and then we should have the add I thing added to the bottom here. So we have a couple of issues. Well, we really have a decision to make. We have to ask ourselves, how do I get this screen to update as a result of something that happens on this screen? Okay. What approach do we use? Go ahead, Charlie.
You can go back to the main activity and change that instruction ET to public static, and you can call it from
Okay. So one possibility is our output text box, right? We can make that guy in the put that guy in a singleton. That way we can update this screen from any other screen. That makes sense? So over on this screen over here, we can say, you know, if it's up in the singleton, we can maybe say something like AR map dot instruction ET dot set text to the whatever, right? All right, so here we can go ahead and do that just as a starting point, and then I'll show you an alternative way. So this dude right here, Charlie wants to get it out of there and put it in AR map and make it public. All right, so then it's no longer called AR map. It's not this dot instruction ET. It's AR map dot. Oh, did I not make it static? You lost your star for the day there, Josh. You earned it, then lost it, all within like 5 minutes. It's terrible. All right, so AR map instruction ET. So we'll find it here. That's setting it up in the singleton. And then any place we use it, we need to make sure we update this. If it was too many more, I would probably just do a search and replace, but we're basically done. Okay. So now what we'll do is inside of this guy, instead of setting this instruction to add things, we don't even need that guy right now, but I'm going to leave him there for a second because I'm going to show you something else. We're going to go ahead, I'm going to steal this. Actually, let me do this. I'm just going to comment this out for right now. So what we'll go ahead and do is we're going to say AR map dot, what's the name of my thing? Instruction ET dot set text equal to AR map dot instruction ET dot, well, actually we probably want to do, we can do append. Actually, that would work. That would be the cleanest thing. I was going to write it as, because we haven't looked at append before. I was going to do this. I was going to say string temp is equal to ARMAP dot instruction ET dot get text dot toString. So now we have the string version of that. Now, if it's currently empty, we can just set it. So we can say something like if temp.length is equal to 0, then we'll say ARMAP dot instruction ET dot set text equal to temp. I'm sorry. Equal to this guy. Else ARMAP dot instruction ET dot set text is equal to temp concatenated with \n concatenated with that. So effectively building your append. Okay. So go ahead and read what's already in there. If it's currently nothing, we only have one line. So go ahead and set the line. Otherwise, go ahead and add it to that guy with the \n. So this kind of reinforces the thing we talked about last time where we're splitting on \n's. We're seeing it happen. All right, and then we will finish. So now this guy should technically meet the requirements. Clear that, go in here, hit add I. So there's our add I dealy thing. We'll add another one. We'll do store. So there's our store at the bottom there. So this is working. All right, so now another way we could have accomplished this. Now, one problem I would point to, obviously this is fine, right? This is a reasonable solution, no big deal. We've kind of talked about the singleton is you want to be careful how much stuff you put up there. All right, so now having a throwaway variable like this, I'm not sure is necessarily any better than just having your edit text up there. You could probably make an argument for, well, if you're putting something up there, you might as well just actually put the edit text. Okay, but we could use the activity lifecycle here. So we already see that in main activity, we get on create gets called for us. There are some other activity lifecycles. So if I just go in here and we'll do a search, Android activity lifecycle. There's some other functions that can get called. So we have on create, on start, on resume. So on resume gets start when user returns to this activity. So we probably could throw this into on resume. Similarly on restart. Well, it looks like on start would always get called too. So we could use on start, on resume. So when our activity is running, we leave that activity to go to that second screen. User returns, oh no, it is on resume. On resume is the place we'd have to put it. Because we're getting to this. I think the activity would not stop unless we left the app and came back in. We'd have to test that. It's possible.
I think it does sometimes
Yeah.
because it'll call on create again.
Yeah. Okay. Oh, it calls on create again? It shouldn't call on create again.
Well, it did occasionally for me when I was testing.
Oh, really?
Yeah, but I ended up doing it a different way.
Yeah.
So I didn't have to.
Yeah. On create should only ever get called once.
That's what I thought. That's why I was a
Yeah.
little surprised when it, because I had a printout in there and I was printing it out again.
Oh, that's weird. Yeah. I can see possibly on start getting called multiple times, but it looks, if I'm following the flow chart here, My feeling is on start should only get called whenever the app really starts. So either it's coming from the background back into, but even that sounds like an on resume. It feels like on resume is the safest.
It would be it.
Yeah, there's probably some testing we can come up with to figure out when exactly these guys get called. But these are different points in time that we can interject stuff into the activity. Go ahead.
So I found something that might also work, which was instead of starting the next activity with start activity.
Oh, you can use it for result.
Right.
Yeah. Yeah. There's a version of intent. There's that you can say where we're going to start an activity for result, and then you can actually that the activity can return a response. In fact, actually, that would probably be the best way of doing it.
Yeah, because if you do it that way, you don't have to use the
Singleton at all. Yeah, you don't have to use a singleton at all then.
So it ends up being
Yeah. So let me do the on resume thing here first. So I'm just gonna, we should be able to just say on resume.
But wouldn't resume get called anytime you come back to that page? So
Yeah, so we'll check.
the memory.
Yeah. The bottom line is I'm going to check against that thing if it's no longer, I mean, this isn't like the best solution in the world.
Right.
It's just an alternative solution.
Okay.
I'm going to check that instruction to add. If it's something other than the empty string, I'll add it. If not, if it's something other than the empty string, I'll add it, then set it to the empty string. That way, whenever I come back to the screen, it just checks to see if do you want me to throw something in there? Kind of make sense? In fact, for time here, so if I say on resume here, that's this one. So that's for a fragment activity. Oh, is there not a resume for normal app compat?
Oh yeah, there's.
It's not popping up here, at least in the documentation I have for fragments.
So it should be on there, which is weird that it's not popping up.
Yeah,
I have an on post resume, but whatever, so here let's just do it on restart for a second, because for time I'm not going to actually probably implement this, but now this guy, he'll get called every single time we come back to this activity. All right, so I can put things in here that change the output of it. Or that, this is part of that life cycle. So now I can have my activity do different things when things start. So on create, this stuff happens exactly one time when this activity is first generated. Some of these other ones, they happen like maybe when you leave the screen and you come back to it. So this guy would happen every single time that event occurs. Stuff like that. Similarly, on pause, maybe you want to stop some download or something like that when you pause the activity. All right, so you can do things like that. And then the last thing that they mentioned was instead of saying start activity like this, we can say this dot start activity, was it for result? Start activity for result. And this guy, will this expand it for me? Yeah. I'm just going to steal that, guys, so I'll pop it into the documentation here real quick. So look at the Java version. So you can create an on activity result function, and this guy will get the result that came back from that intent. So you can give it a result code, a request code, and a result code to find out which response it's coming back from, but you can actually just hide your response inside of your intent. You can add it as an extra to your intent, like the string you want to add, and then this function will automatically get called when that activity ends to give you that result back. So that would probably be the best solution here, since it would keep you from using the singleton at all. That makes sense? All right, so a couple different ways of accomplishing it. Given the size of the application, what we did was clean enough. Questions, comments, concerns, bribes? Okay, so I'll put this final version up on GitHub in case you want to show it to anybody or try to expand on it. And I will see everybody on Thursday at 1:10 p.m., right?
I was not expecting you to have notifications enabled during class.
Oh, it's fine.
It was enabled during the movie too.
That's true.
Really?
Wait, you did?